We're live. We are indeed. So welcome. Today is a Lightning Talks day. I'll keep my intro to like 45 seconds. We had tons of small topics to cover. Small does not mean small in content. Small means the optimal bite-sized duration to entertain people and make it useful and to make you guys want to read deeper into the topic. There are tons of topics where we can do it in like 20 minutes or less. So we got 3 speakers today. Thank you, folks. And with no further delay, the mic goes to David talking about WebAssembly. Wasm.
Great. And I just realized this Wasm, I've been trying to find all the instances where I put all capital letters like it's an acronym, which it's not. It should be capital W only and lowercase asm. But this is building high performance applications with Wasm, WebAssembly, and JavaScript. So, as you know, modern web apps are demanding, and JavaScript is powerful, but not always the most efficient for CPU-intensive tasks. And so that's where WebAssembly can come in, and you can have near-native performance in the browser. So what is WebAssembly? Binary instruction format that runs at near-native speed. It's designed for performance and security. Performance because of the near-native speed, and security because it is sandbox. In other words, it doesn't have full access to the host runtime. For example, anything that has access to has to be given explicitly to it, like file system or browser APIs. And it works alongside JavaScript. It does not replace JavaScript. And you can run it inside of JavaScript in the browser and in node.js, which I'm going to show later. And it can be written in C, C++, Rust, Go, I'm sure some other things, but they compile to WebAssembly. So JavaScript has this execution model being single-threaded and just-in-time optimized. And the WebAssembly execution model is pre-compiled to bytecode, and it's also just-in-time optimized in V8. So, and actually, I don't know how to access my comments, but I have this comment here. We can read the docs in the WebAssembly compilation pipeline. So in WebAssembly, first, and JavaScript does the same thing. It has this sort of liftoff, which is a one-pass compiler. So this will take the WebAssembly bytecode and compile it into machine code. And it's just one pass, it's not optimized. Then you have turbofan, which V8 will take the non-optimized code and it'll identify hot functions, which are functions which are just run a lot. So there's some threshold, and these hot functions will be passed to the turbofan compiler, which is a multi-pass compiler, which will optimize the code. So that could be making assumptions about the parameters that are being called, the parameters that are being used in functions. It's only using an integer, for example, or you can inline functions, things like that. So this is what turbofan does and optimizes this code, and does this for JavaScript and the WebAssembly bytecode. So let me go back to slideshow. And so it runs in a sandbox, and I say in V8 here, JIT optimized in V8 because that's the only engine that I've been looking at, but I'm pretty sure all the other engines will also do that. But don't quote me on that. But here it runs in a sandbox, so it interacts with the world only through provided APIs, like JS functions, the WebAssembly system interface. Yeah, and then performance benefits, predictable execution. I initially thought there was no garbage collector, but then there is, and so it's enabled by default in Chrome now, which I haven't looked into it all, but it seems pretty cool. So you can compile Java, for example, and have your garbage collector. Okay, and so this is an article that Dima sent me, actually. Wasm will replace containers. So it's a true write once, run anywhere experience. And then I was also looking at this American Express. They have this really good talk too about replacing containers with WebAssembly. So it's very interesting stuff. And so why would that happen? Well, it's portable. So anywhere that runs V8, which is a lot of places, can also run WebAssembly. And the WebAssembly system interface is developing rapidly, and that's good. You can run WebAssembly directly in the browser also. So it's portable in the sense that you can run in the browser, and you can also run it anywhere that there is a V8 runtime. Microservices. So in this paper, or in this article, Wasm will replace containers. It talks about Cloudflare workers, which are serverless functions. And so he talks about a big improvement in terms of not having network calls. If you have a bunch of containers and you want to call another container, that's a network call. Whereas in V8, you have this concept of an isolate, which is isolated. So you have, and actually, this is some issue I'm tracking in V8, but this is a really good description here. So the isolates in a process share the same 4 GB heap cage, and the heap is organized in pages of 256 kilobytes, and each page belongs to one isolate. Isolates can execute concurrently in different threads. So you have this same 4 GB overhead. This is not shared memory. All the isolates have these pages of 256, and they are isolated. They only use that. So this is just some overhead for all the isolates. And then in the actual V8 runtime, to spin up another isolate, or for example, in the instance of Cloudflare workers, spin up another function, it can happen almost instantaneously, and you can have more with the same overhead for the runtime. Whereas this is traditional architecture, I have a bunch of overhead for each function, and this is the workers V8 isolate. And this comes directly from the Cloudflare documentation. So hopefully that's clear. Okay, when to use WebAssembly instead of JavaScript. For DOM manipulation, JavaScript is generally good. And it's a little bit slower with WebAssembly, specifically because of the foreign function interface. So passing, going back and forth in the JS WebAssembly boundary, and especially if you are using non-shared memory, so you're manipulating memory and sending it back. So that slows things down. There's overhead to doing all that. What WebAssembly is good at is, all of these things that require CPU intensive tasks. So Conway's Game of Life, it predates LeetCode, of course, but it's, long story short, is you're given a grid, and you're given a grid of ones and zeros, and the ones are alive and the zeros are dead. And based off of these rules, to get to the next iteration of the board, you follow these rules, which will tell you if a certain cell is dead or alive in the next update. So I'm not going to go through these rules, but basically that's the gist of it. And so we can write code. I'm going to talk about the memory here in a little bit. But here in this optimized Game of Life version, we have this pointer, which is in WebAssembly, you have linear memory, which is just a contiguous block of memory, and it is an uninterpreted set of bytes. So here we have this pointer that we have to reinterpret to a cast. We have to reinterpret or cast as an integer pointer. So we're sort of just making that assumption here. And I'm gonna talk about the memory and pointers in a little bit. But here you have the in script and bindings, which, this is how you export. Essentially, this is how you export, C++ functions. And then you compile it, and then the compiled WebAssembly will have these available for JavaScript. And this is compile step. And then you can load WebAssembly in Node with a simple require, and you can load it in React too. So we have this, it returns a promise that resolves to the WebAssembly instance. Then you have zero copy memory access. Okay, so WebAssembly does not have access to anything outside of its sandbox. So it can declare its own memory buffers, cannot access anything outside of that environment unless it's explicitly allowed. So browser API, system files, libraries, devices. And two ways communicating between Wasm module and the host runtime, which we'll see here in a minute. Arguments and return values from invoking imported and exported function. So passing back and forth, for example, a pointer. And then limited to exchanging fundamental WebAssembly types is I32, I64, F32, F64. Like I was saying before, WebAssembly only sees these uninterpreted bytes, which is a thing of bytes, and to do anything with it in WebAssembly, you would need to access it. There's specific APIs for accessing different data types. But with but in C++, we can, like I was showing earlier, we can reinterpret a pointer cast or reinterpret a set of bytes as a pointer. And so using WebAssembly memory, so raw WebAssembly memory can be used to pass non-fundamental data types between runtimes. And so all these things. And you can use a combination of the two. So you can pass pointers and arguments, and in Wasm and in JavaScript, you can update the actual memory that the pointer is pointing to and simply pass the pointer back and forth. And so hopefully that makes sense. And then we can compare the Wasm. And I don't know how I'm doing on time. I've been trying to talk really fast.
You're doing great, don't worry.
Okay, great. Okay, so we have this Wasm game of life and this JS game of life that's running in a React component. I lost my, okay. Here we can see, well, first of all, let me move this down so you can actually see game of life. So this is a 20 by 20 board, and every time, sorry, this is actually, I was profiling this, running it 1,000 times, but let me go step by step. So that's game of life. And this React scan shows every re-render, but that's what the game of life is. So that's the least interesting part of this, but just to show it. So we have this JS game of life, which calls this game of life function from this game of life.ts file here. So it's just TypeScript, and it gets compiled down to JavaScript, which is what it's using directly here. Then we also have a WebAssembly version of the same thing, except this WebAssembly version has been compiled down from this C++. So that's what's happening. So here we can do performance here. So we'll click this a couple times, stop. And this is the TypeScript version. And these, I clicked it 3 times. These 3 little yellow humps are the clicks. And we can see here, if we, let me move this down. Yeah, we can see here, if I zoom in on this specific click, this game of life. This is the call stack. The call stack. You can see this chain of calls leading to this game of life call, which is called a couple times. Well, it's called 1,000 times, but you can see here. And so this game of life, in total, takes about 100 milliseconds. And this is the JavaScript version, and we can see the memory. If you see here, like up here in this area, it'll highlight where I'm hovering over. So the yellow part is the actual execution of game of life, right? And you see the memory, which is this bottom area. This is the JavaScript heap. The memory doesn't really change much until afterwards. And that's when you update the actual board. So the actual re-rendering and painting and so forth. So that makes sense. And here we can see this JS heap is at 5,800,000, 40, 31, 40, 58. And I'll actually open this up so we can see the WebAssembly version. So it's the same exact thing, but we're going to profile it here. I clicked it 3 times, so we can come into here. Here, this you can see that there's this chain of calls, this JS to Wasm. The update board is the actual TypeScript function here, update board. So you call this update board, that's 34 seconds. And then the JS to Wasm, well, the whole thing takes 34 seconds. So it's 34 seconds, which
milliseconds.
Milliseconds, yes, sorry. The whole thing is 34 milliseconds, whereas this was about 105 milliseconds. So you can see there's a speed up in terms of the WebAssembly use. And let's look at the memory. Well, okay, it uses actually a little bit more memory, 75. This is 31, 40, 58.
But it's not a clear comparison. Well, WebAssembly runtime would allocate more than needed.
Yeah. Okay, yeah, that makes sense. Well, in any case, it's faster. At least we know that. And then we can also run it in, I have this other version of it, which just runs in Node. And this is a 10 by 10 grid. And this is running 100,000 times. I was trying to do it in the browser too, but then at like 10,000, the browser started being really weird and crashing. So I stopped doing that. But this is 100,000 times for WebAssembly and JS. So the JS version, 48 milliseconds, and the WebAssembly version is 19 milliseconds for 100,000 re-updates of the board. Yeah, I think that's all I wanted to show. And then, like I was saying, the WebAssembly system interface is cool. You can have garbage collection, which is something I still need to dig into myself. You can do AI, ML in the browser. So, yeah, if you want to add me on LinkedIn, please do. And this, I think, is like a leak code group on Telegram if you want to join. So that's it.
This was super cool. I got add a couple things. I think you allocate memory on a stack in the C++ code. If it's global or passed from the runtime, it could be even faster. Yeah, this is super slick and chill. And I did not know some of the debugging tools for like in the browser. All this flame cross, they're fantastic. I do want to add one thing though. Since I officially entered the Web3 space last year, one of the popular runtimes is called Substrate, the Substrate framework. Polkadot is based on it. And it turns out WebAssembly is widely used there as this JIT compiled logic. There's literally the core logic is in Rust, but the embeddable logic is WebAssembly. And it turns out the guys who run that, who build it, who maintain it, they found tons of clever ways to use WebAssembly. You can literally upgrade the code with zero downtime. Each node has its own index. So like you need to write this evolution code that transforms the old data format to new data format. And then all the nodes, all the blockchain nodes atomically switch at certain lock index to the new runtime of Wasm. And they have this thing called host functions. So Wasm calls into the host. And as long as you only update the Wasm, it's zero downtime. So like every node runner just runs the node and it works. So I do believe WebAssembly is going to be the future. I looked into it a couple of years ago. I used it. I looked into it again a couple of weeks ago. It's less mature than I would expect. I mean, WebAssembly, like between Golang and C++ are different WebAssemblies somehow. But yeah, the claim that you can do it in the browser and locally and from like a Rust outer shell, this is so super cool. People seem to like it.
Yes, I think it's really cool.
Yeah, it would be awesome to connect our careers to WebAssembly somehow. That must be fun to work with. All right. Yeah. Thanks, David. Oh, what? I think the I'm using a Mac finally, and I think it can do stuff like this. Can it? It can. Yeah, well done. I guess I will do my part real quick. Oh, you guys cannot see my screen yet.
No.
Well, now you can.
Yeah.
Let me do the magic for all of us to be here. All right. So I'll be quick. So it's somewhat ironic that sometimes you have to talk about some things and do it for many, many years until we can phrase it cleanly. So I'm a big advocate of stuff like event sourcing, immutability, source of truth, like signing stuff with hashes so that the past never changes. And eventually I've realized maybe there is a short way to explain this that is not too nerdy, that non-hardcore backend engineers can relate to. And I found that event sourcing is hard to explain to an uninitiated brain. But source of truth, it could be the easiest first concept. And I'm going to experiment with a way to introduce you guys to it today. So I guess I'll put you guys to the right. Like this. I will put you guys to the right like this. And I'll hide myself too. Well, I need to close this. Hold on. Oh, good. So I never really planned to quote Eliezer Yudkowsky, but I think of his essays, there was one that I really liked. The setup is that the essay introduces the reader to the concept of counting as the revolutionary thingy in the history of humankind. Basically, the idea is that the story setting is that there's a shepherd who needs to shepherd sheep, and the entire community is dependent on these sheep being shepherded and not eaten by wolves. And once the number of sheep grows, it's not like 3, it's more like 100. You need to count them as they get back to you, because if you did not get all the sheep back before you close the gate for the night, even a small chance that a sheep is gone, day after day, results in an existential threat for the community, right? And the essay talks about the shepherd who realized that you can do the invariant. What he does is you have this gated location for sheep, and you have a bucket of pebbles, of small stones or small rocks. And every time the sheep goes out in the morning, you put a rock there, put a pebble there. Every time the sheep comes back, you take it out. So that once the bucket is empty, you know all the sheep that went out went back in. And it sounds super trivial to us today because we know how to count. But Yudkowsky makes a point that it's really not that trivial back then. And the story goes as there's somebody from the authority shows up and he says, I'm gonna take this away from you because no like your hands are not worthy of handling this magical, super powerful thingy, and then this person from the government is confused because he doesn't understand what the magic is. Are these pebbles magic? No. Is the bucket magic? No. You can literally examine the rocks. I can take the pebble out of the bucket. I can give it to you. As long as I put a different pebble into the bucket, as long as the invariant stays true, the machine is good to go. And that's pretty much, it's a long essay, it's Yudkowsky. But he pretty much talks about how the untrained brain is having trouble comprehending this. But of course, today we all know how to count. We cannot imagine the civilization that does not know how to count. And I'm going to make a strong claim that knowing how the source of truth of data works is something that we as the engineering community worldwide need to learn somehow. I think it's slow to getting there, but too slowly to my taste. So I want to play my small part. And my claim is that learning to think in source of truth is like learning how to count. Once you do it, once you learn it, you cannot unlearn it. It's hard to teach, but once, like, a community of people who understand what source of truth is when it comes to designing software, we are just so much better equipped at not making mistakes. So we can talk about event sourcing, consistency, two-phase commits, reliability, sagas, but it's all, like, I was looking for a simple way to explain this, and the source of truth probably is. And by the way, I've converged to using dashes. Source of truth is a single word. I believe it's proper English, even though it's it's not proper English in America, but I believe it's proper English in terms of making people remember this as a singular term. When people talk about source of truth, first of all, we need to realize it's logical. It's never physical, because if it's physical, it's like Einsteinian relativistic physics. You cannot possibly make the change concurrently in two different locations. It violates the laws of the universe. So if you say my source of truth for this data is this hard drive, or this jump drive, this flash drive, this USB stick, it cannot work, because if you lose it, or if it's corrupted, the data is gone. And if it's on two USB sticks or two hard drives, then of course there's no way to atomically update both of them at the same time. So there will be some, if you need them to be consistent, identical with each other, you need some software logic, so that the physical contents of two locations may not be the same. But with respect to the API, with respect to the contract that you can use to access and modify this data, it acts as a singular source of truth entity. So the first lesson, the first brain adjustment is to understand the source of truth has to be a logical concept. It cannot apply to physical bits or physical devices. It has to apply to the agreement on how we use the data. And then once you internalize this, you can use mathematical proofs that certain algorithms mutate the data in ways that guarantee that with respect to the allowable GET requests, the data is consistent in and of itself. So yeah, it's all about the entire system. And the sad truth is that we're all engineers, whether we like it or not. Engineers get paid by the real world companies and projects. So eventually the business interests come first, and eventually the boss tells us we need to ship this feature for this customer. And what suffers first, in my experience, is always the consistency of the data, because source of truth as a concept is not fully internalized by the entire company, and then some hacks are introduced here and there. And these hacks, when it comes to source of truth, are exactly what makes progress, makes code evolution slower. So I'm here to try to spread the word on how to reason about this in the terms that make it less likely that your company follows the unfortunate path. So much like with the pebbles in Yudkowsky essay, what makes the magic? And it's going to be a strong statement. It's going to be a bold statement. I might regret it later, but for the purposes of this conversation, I might as well make a bold statement. I think if you think of top criteria, top arguments, top parameters, I would say the first one is consistency or correctness. And I call it CRC for 3 letters. Consistency or correctness is that whatever your system produces would never confuse the user. So if you want to transfer the money and your application told you transfer is done, here's your confirmation code, it is guaranteed to be done. It's guaranteed that the other person is going to receive it. It's guaranteed that your account is going to reflect the deduction exactly once, not less, not more. To me, consistency comes first. Resiliency, the R, or durability, to me they almost mean the same thing architecturally, is that the replication factor of the data is high enough. So like a single machine, a single hard drive, a single data center location suddenly disappearing, or at least being offline for a while, does not affect your system. And the third one, I would argue that's compliance. I would argue that's what most small company engineers don't get. That sometimes it's actually important to obey some rules that may not sound reasonable, and you have to spend a lot of time doing things that are totally useless for the end user. But in order to be a big company running across countries, across continents, you sort of have to follow all this, no matter how ineffective it sounds, because that's how the world works today. Consistency, I believe, is that if something happened, it happened, and vice versa. I'm not going to go all Klapman here. The book is really amazing, designing data-intensive applications. But basically, if you can fully assign like a sequence ID to every single mutation, you can always reproduce the stream of events, and it's going to be guaranteed consistent state at any point of time. That's event sourcing, more or less. Most companies I'm familiar with are not ready to go there. So it's going to take like another decade or so until it's widely adopted. But at the very least, we can say that your unit regression integration tests should stress test your system that no inconsistent responses come out. You spam it with requests, you kill machines randomly, and it can fail, it can time out, but it should not give you inconsistent results. That is probably something I personally care for a lot, even though in real life some systems do not have to be consistent. It's a famous example that we don't have much time for that, but it's a famous example that sometimes introducing like extra developer years into making it more consistent than it needs to be is just not worth it, because this inconsistency once every 10 years costs the company $100 on gift cards. So why bother? But still, like for important stuff, I think consistency is key, especially when it comes to something like infrastructure, which nodes run what, because a mistake there can result in the entire cluster and the entire operations collapsing, and then manually recovering the data is super painful. Hopefully we use cloud primitives these days to never have to do it, but it still is an issue. For the second thing, resilience or durability, that is something that you learn after being in the industry for many, many years. There are theoretical guarantees and there are practical guarantees. Like in theory, TCP/IP, unlike UDP, guarantees that packets will be delivered. But in practice, it never is true. Like your network card can die, your cable can be unplugged, you can have a power outage on the city level. So guarantee is ephemeral. The truth is, you don't need to focus on guarantees, like mathematically speaking. You need to focus on good enough guarantees. And if you start with consistency and start with source of truth, lack of sufficient guarantees in resiliency is actually not too bad, because you can always reproduce the state, like reconstruct it later from a backup. I'll touch on the blockchain eventually. That seems to be a perfect example. Whether we like it or not, I'm not going to go into this deeply. If there's a block that confirms that some things happened, enough machines on the planet have these blocks hashed and can reconstruct it, so it's guaranteed to be correct. So once consistency is there, durability is easy to add. Vice versa, not always true. And compliance is like safety third, speaking in layman terms. If you want to launch in Europe, you have to support GDPR and right to be forgotten, which is surprisingly hard with like data residency rules. Oh, this user is from Germany, so you have to store their data on German servers only. Otherwise, the German regulator can like sue your company and force you to close operations in the country. So you have to think of this all the time. I have some experience working within the gambling industry. So acquiring licenses for gambling is the biggest issue for the business. So building software, it's not about optimizing the code. It's about making sure your data flows are clean enough so that once a new country, a new region, new regulator asks you to send certain reports within certain timeframes, within certain guarantees, your data model is good enough so that you can do it quickly and not within like a year. Security perimeters, audit, bring your own keys, all the cool stuff. And that's something that many engineers who are early in their careers would be frustrated about, because it sounds like, hey, we could spend like a month building features, but instead we're going to spend a year doing something that the user does not notice. If you have a small startup, yes. If you work for a big company and the money is there, so most of us most likely will somehow touch big companies, so to speak, you have to embrace this. Otherwise, it's not going to work the other way around. And when I talk about consistency and source of truth, the example of sending funds, I don't like the word money or tokens, but let's say you want to send funds. It's surprisingly illustrative in terms of from this from the setup that you just need to send something from Alice to Bob. Let's say Bob needs to pay the rent, and somehow right now Bob's account is insufficient balance to pay the rent, but Alice is returning Bob some loan or whatnot, and only after Alice has sent Bob this amount, Bob has enough to pay the rent. This trivial example is extremely good at generalizing what is the issue with consistency, with consensus, with source of truth. And it also turns out that, in my experience, if you understand this well from first principles, you'll be well equipped to talk about this in interviews and real work, so it's useful. So just a couple steps from the baseline layer of you need to send tokens from A to B, or funds or whatnot. So level 0, you just store accounts, could be SQL table, and you can introduce a transfer. If neither account, if the account that you're debiting does not go below 0, you send a transfer, instantly finalized. That's trivial. And then someone says, oh, you know what, you can go negative. That's fine, you have a credit line. So there's a separate field, like optional int or whatnot, that you can go down by up to this amount, and then the invariant is held. You are allowed to. And then the business requirement changes again and says, well, some transactions you cannot run. So Alice cannot send tokens to Bob because Bob is blacklisted. And then I have the anti-fraud department, so that some accounts, some transfers are not instant. In the world of traditional banking, it could take days, but even in KYC Web3, it could take hours. So suddenly, again, your invariant may well be broken, which is painful. And then eventually some other boss comes and says, you need to revert transactions. And then you can receive something, send other people, and then this incoming payment is reversed and you're negative below your limit. And every single step is painful unless you think of source of truth first. If you think of invariance first, of what the data invalidation looks like, you can build a resilient system. If you think of, I just need to have this if statement and hopefully it works, you have no idea which part of the system is going to break after something is invalidated. So thinking of source of truth and invariance, make sure your system can be data integrity first, which I can guarantee you personally will show up a couple of years down the road. The interesting part is that thinking in source of truth terms, forget event sourcing, forget consistency. Thinking in terms of source of truth immediately makes hard problems pop out. So you can quickly see what is easy and what is hard. For example, if something cannot change, if some data is either not in the system or in the system, and if it's in the system, you cannot mutate it. That's like a torrent protocol, right? You have the hash, you want to restore the file from the hash. Either you have a file from the hash or you do not. If the hash is cryptographically secure, that is almost guaranteed that if you have a file with this hash, that's the correct file. So if you just need to distribute some data, gossip, hashes, it just works. It's a trivial problem. There's no room for lack of source of truth. There's no room for issues. If something can only change in ways that do not depend on the order of operations. Sending tokens, maintaining the invariant that it never goes negative, that's a tricky part because the order suddenly matters. But something like the counter that only goes up, it doesn't matter in which order you apply the increments. You can even batch them, like per region, per node, per machine, per data center. So that's where CRDTs come to the rescue, and it's also a trivial problem. Now, if you need to change something, but this change only depends on this object itself. So the condition that this object can go from this version to the next version does not imply invariance on any other objects. Then I would not say it's trivial because we're entering this total order broadcast territory. But if you only need to check this particular object's state, this architectural concept of if unmodified since, you only change this object if you're still looking at the latest version, and it's an atomic operation. If my version is 41 with the same hash, make it 42 with different hash. And the system either tells you, yes, it has changed, in which case it's changed for everybody, and nobody can branch it out. There's only a main branch of every key element. Either it does change or it does not change. And if it does not change, you just retry the transaction on your side. That is also extremely possible if you cannot rewrite history. If you have a rewrite history, that's a totally different topic. Let's not go there. So I would argue that even consensus-based solutions are commodity these days. You don't need to invent the wheel. You can just reuse what I would say 5 years ago is Kafka. Use a single topic, single partition Kafka for total order, and then apply mutations in the order, and you're guaranteed to be successful. Today we have widespread Raft protocol, Even Kafka is based on Raft. Alex will talk about this soon, about etcd. But that's like, if you see the issue with this in your system and the throughput is not too high, just go ahead, use etcd or Kafka, and you'll be fine. The issue is that if something is a long-lasting transaction that requires preconditions from multiple parts of the system to be satisfied and should happen exactly once, that's where the painful part begins. That's where you need to be very careful with your implementation. That's where sagas, two-phase commits, compensating transactions, all these painful concepts emerge. And again, SysDesign wise, you can do it, but if you think of source of truth and invariance, life becomes easier. We do witness this emergence of new concept called durable execution. Temporal, coming from Cadence, is a good example of a product that guarantees certain invariance. I would say it's a step in the right direction towards source of truth. Temporal does not run like OLTP transactions yet. It's mostly for slow operations, like slow, long-lasting. But it's like, once the world gets there, I believe we will, like, eventually we're going to flip to the world where people think in source of truth, and we'll never look back. Much like we do not need to write assembly code once we have good high-level languages. I want to mention the blockchain here because I'm not a huge fan, for the record. I'm not just saying that's the future and we're going to all live on the blockchain eventually. But the community, from the system architecture standpoint, apparently, like, I dove into this last year, apparently the community has done a lot of things right. They know how to count. That's the point I'm trying to make. In terms of source of truth, the blockchain forced people to adjust their brains faster. So for instance, this idea that once the block is finalized, the hash is broadcast to everybody and it contains the data that cannot be altered. Surprisingly, that's exactly what most large companies lack. Like, I've been to many big companies, and where most time is spent of engineers and managers and whatnot is exactly the issues that could have been avoided had there been a similar blockchain-like concept internally in the company. I'm not saying every company is going to have a blockchain in-house. That's not going to happen. But enough people thinking in terms of finalizing transactions for good and having them replayable will change the world. Event sourcing is what I used to say for many years, and now I'm slowly realizing it's not the phrase you can sell easily. If you say event sourcing, architects would like you, CTO would not. If you say source of truth and guarantees and invariance, this does take you places. So I encourage people to think in these terms. Yeah, I guess that's my lightning talk. Knowing how to count is easy. Teaching people how to count, surprisingly difficult. But once you know how to count, you cannot unlearn it. So let's all learn to count and then spread this doctrine, whatever, religion, further. One of the best changes I've seen in myself and other people I work with is, once you know how to count, you don't talk about databases. So in SysDesign principles, you have like, you have a database and a cache. That's correct. I'm not saying it's wrong. But if you think in these terms, you're setting yourself up for a failure. Instead think of data contracts and think of invariance. So whether it's stored in a cache, in a durable cache, in a database, whether it's in-memory view of some event log stored in Kafka or etcd, that's immaterial. As long as you define data contracts first, you'll be fine. As long as you think of source of truth first, you'll think of data contracts first. The next big change is backwards compatibility. Think back to the example of Alice and Bob sending tokens to each other, and you need to like introduce some concept of transaction reversal. If you do it in a hacky way, the invariant that some balance cannot be negative or below the credit limit will eventually be broken somehow. So the backwards compatible code, like speaking in low-level programming terms, if some code assumes the invariant holds and suddenly it's broken in data, you're going to have undefined behavior. The whole like hell can break loose. Even if you use proper languages, your undefined behavior would be in your own if statements because you assume the if statement cannot fail. If you have to force yourself to think in backwards compatibility terms first, like no change can happen unless all the code I wrote before is guaranteed to be compatible with whatever invariance this new code breaks, you'll just make 2 rollouts or 3 rollouts instead of 1. But they will be quick, they will be simple, painless, and in the future, nobody can make this mistake again. No issues will proliferate, which is super, super awesome. Well, and finally, I do want to say that we do live in the world where business requirements come first. It's hard to say no to the boss, to the CEO who says we need to launch this. But I think slowly but surely we're getting to the world where talking back in terms of, hey, if we just do it, as you say, we can do it in like half an hour. If we just do it in half an hour, we're going to break stuff because A, B, C, D. And here are real examples with real data. So let's give us a day to think it through. I hope that's it. I hope that's the shortest version of what I could do with this. Questions? All right, we're good. Which means we have enough time for Alex to take over.
Great. Can you hear me well? Cool.
Yeah.
Maybe send to the chat link first.
I'm recording my screen, so I'm not gonna open the chat, but you can share yours.
Okay. Yeah. We'll do this. Why it doesn't? Okay, now you probably should see it. Do you see it? Right? Cool.
Yeah.
Okay. As Dmitry said, what I want to talk about, I want to talk about a building block for consensus or for leader election. So if, for example, you don't have a very, very performant system, you might use some other tools that might be not created directly for this, but still they are quite good. As Dima mentioned, you can use Kafka, you can use console, you can use actually any other key value store which supports comprehensive operation. And here we will go briefly and talk about etcd, how what it can offer us. And it's interesting thing because it allows us to do leader election thing, and it has nice watch API, so you can watch who is the leader if something was updated or changed, and you can re-elect. So it's actually quite a powerful building block for the system, where you can quite cheaper get quite interesting things. Yeah, so how many operations? As mentioned before, it's the user's raft, and as we know, raft requires at least one round trip to confirm the transaction. So, which means that, for example, if you are operating in one data center, you can have theoretical maximum of 500, 1000, something like this, confirmed transactions per second. And these are numbers inside one region and cross region, right? So you can see that it's good enough, but not huge amount of operations, right? So if these numbers are good enough for you, then yeah, probably that everything's great, and you can just do it one by one. But if you can't do this, and if you want to be a bit more performed, you need to still you don't want to implement Raft yourself, right? And you need to start making some tricky things like batching your transactions. You need to pre-store them somewhere. You need to make sure that they're durably stored. You need to think, okay, when exactly now you can send the confirmation to the requester. And yeah, this is like intro, and now I just want to show like few lines of code which I did. Yeah, so what we have here, what we have here, we have it's the cluster in Docker. We have 3 nodes, exactly the same, right? So up and running. Just checking that. Yeah, okay, that's good. Now you can check what we have. Yeah, we see that we have the leader. By the way, is font big enough?
I can see.
That's good, yeah.
Yeah. Okay, cool. Yeah. So now you see that okay, we have the leader, right? And first, what I want to show is how it's actually easy to do leader election. I will uncomment this for a while, right? And what happens here? We have etcd endpoints which we want to connect. We have client. Then when we create a client, we start to campaign. And how campaign looks like? How campaign looks like? Okay, I need to. Yeah. Okay. Now, how campaign looks like?
Okay.
So you take a list.
Can I just confirm real quick? You're not talking about etcd
Sure.
internal leader elections. You want to have your own your software.
Yeah.
So you
Yeah,
you're solving the problem of
that's
leader
it.
elections through etcd.
Yeah. etcd has its own leader election process. It has Raft and stuff like pings, hidden bits, etc., etc., etc. But right now we want to just get leader election on our side, right? In our system, but we don't want to implement all this complicated things. I mean, it is not like extremely complicated, right? Because you have cool implementations of Raft almost in every language, but still it's much harder than just use few API calls. Okay, so how it works? So you take the list, right? And lease is something like, if you're familiar with Zookeeper, it's like ephemeral node. So it lives until your client is alive. So when your client goes down, you have timeout. After this timeout, this list is destroyed. And what's good? Everything that you put into etcd storage with that list will be deleted as well. So that's how actually, I mean, kind of through this process, that's how other nodes can understand that, okay, leadership has been lost. So let's try to run it. So when you write something in etcd, you need to use like keys, obviously. And right now for leader, I would use that key. And in one window, I have this command. So what it does, it watches for any update that we have by this key, right? And now if I just run this code, it will try to perform leader election. And we will see updates here for the. Okay, I need to. Not what I wanted to show. No, 1 second is. Okay, so we got leader, right? And we have node 1, right? And then the question is how the nodes can understand that, how other nodes can understand that the leader fallen. They watch for updates for this key, and if I kill my client, we have timeout in 3 seconds here, and in like roughly 3 seconds we will get notification here that okay, leader died, and we can react on it somehow. We can try to campaign again, etc., etc., right? So this is about leader election. So like super easy actually, right? And then now I want to show you how like performant ish. its CD can be. So right now, what I'm going to do, I'm going to just write this, run this code. What it does, it goes to this prefix with individual. Then it takes some time as like just another part of the key, and then it just starts to spam, let's say, transactions or some values, right? So it just increments the counter and just populates something on it, and it does it in transactional way, right? So it checks who is the leader, and it checks that the leader is still here, and it just writes transaction by transaction, and then I just write that how many transactions we have, right? So if I run this again, I can see that yeah, it should start. Okay, I didn't save this file. Start again. Yeah, so it starts to write transactions. So you can see that everything happens on my Mac. It is not the most performant hardware, but still, the biggest advantage here is that you don't have any network delays right now. So you have approximately like 1,000 transactions in like 4.3 seconds, something, right? Which is quite good. Then I need to introduce delay, for example. Okay. Okay. I need to install it first. Yeah. Let's wait a bit. So I use utility traffic control for
hot patch and live containers. That should be in the
yeah.
in the Docker file.
Yeah, should be. Obviously. Yeah, so using traffic control utility for introducing delays. Why? Okay, doesn't matter. I think it still should work. So in that case, I introduce a 10 milliseconds delay for each node. So each node will send like will buffer, let's say, request and send them 10 seconds later. So if I run the same code again, I can see that that's much slower. It's like 10 times slower, almost, right? And in that case, we are talking about like 10 milliseconds delay. So we're talking about 20 milliseconds round trip. So it's relatively low, probably between like two data centers in one region. Maybe you can have this. Sometimes it depends. But if, for example, you have data centers in different regions, so 25 milliseconds, 50 milliseconds for each round trip. So approximately we should have like 20, right? Yeah, 20, around 20 transactions per second. So what we have here, and it becomes slow. And again, sometimes that might be enough, but if it is not enough, what we can do, we can do transactions. And again, in that code, what I do batch for transactions. There is like an environment variable where you can override amount of maximum allowed transactions. By default, it's 128 transactions per write. Oh, not transactions, operations per write. And what I do here, I create exactly the same operations and just batch them into one transaction. So, and again, I don't change delay. It's still 50 milliseconds for round trip. So if I run it now, we can see. Okay, I again forgot to press command save. Yeah, so you can see that now is like way quicker. It is even way quicker than it was before, with one transaction with zero delays, right? So I mean that's kind of obvious, but it's cool, and it's really cool that it's really easy to use it for some of applications where you still need performance, but it should be not extreme, but relatively good. So like how much? Approximately 1,500 transactions per second. Sounds good. So if you have relatively small transactions, if you have relatively small operations, you can increase this number, for example, and can get even better numbers. Yeah. So quite good. Yeah, I think that's it. What I wanted to show you. Do you have any questions?
Did you mention if there is a? So sorry, you were gonna. Did you mention if there was a maximum transaction per batch?
Yeah, maximum operations per batch. By default, it's 128, but you can change it. But again, there should be some balance, because, for example, if your operations are big, then probably you can't just increase it, because you need time to deliver the message, and you will suffer. So in real life system, you probably need to test what you have and find the optimal.
Thank you.
I think these talkers are kind of worms, because there are so many cool things you can do with etcd. The consensus part, the most important part, is that all the updates are transactional. So this invariant holds. If the node is not a leader, it cannot make changes. But then your transaction batch updates different keys by design, which is only useful if you want to use etcd native ways to access that data, like get per key or subscribe to a given key. Nothing blocks you from batching transactions logically in your code into the same etcd key, in theory. If you do not need to watch particular keys or like get granularly, you're good to go. So yeah, the biggest message I think here is that if you need some basic consensus, you do not need Raft. The leader of the cluster itself, what Alex showed at the beginning, this ASCII art table with the leader true, like that's concealed from you. You ideally want to talk to the leader because it's faster round trip time wise, but most languages have etcd clients that would send your transactions to the leader itself, and then you can just operate with it as if it's a singular system of a couple of machines, and they orchestrate between themselves, which is super cool. It's not a database, don't get me wrong. It has limits on settlement times, it has limits on the size, but for stuff like metadata, like orchestration workflows, that's good enough. Thanks, Alex.
Yeah, about sending to the leader. I'm not like 100% sure, but I'm quite sure that for consistent read, you don't send to the leader, you do quorum read plus leader.
Well, yes, but then again, thinking in sort of truth terms, if you know how to count, you never do consistent reads unless you need to do a write afterwards, and your write is a transaction with a cluster. So if you're reading, you're content with potentially reading past data, as long as it's guaranteed to be correct. And if you want it to be consistent, it's identical to a mutation. Like imagine you need to mutate like a number of reads for a given key. This has to have its own sequence number that has to go through the consensus. This has to be hitting the leader first, and that solves the problem. All right. I guess ideally all the dots connect. I can totally see how these three talks connect in a nice product slash service slash something fun to build on, to work on. Yeah. By the way, I would say that like Golang is a good language to work with etcd because etcd itself is written in Golang. Although I looked into the APIs, the Rust API is as clean. I would say that like ideally you would like to have some DSL because right now the transaction guarantees that only the leader can make changes. That's coded in like in your head. It's not verbalized in the code. So if that's your production code in your company, some more junior engineer who doesn't know this leader check must happen may break it. Or then you like have some rules on who can be leaders and you need to manually update the code. With proper defensive coding, you can make it redundant, as in it's guaranteed to be correct logically, which would be super cool. Topic for the next talk, I guess. So thank you. I guess we can declare this day a success. I think in the recording of my screen, I've been moving the avatars here and there to see more of the screen. So lesson learned. I can do better eventually, but we should be fine. I'm pretty sure we're fine.
But did you record your screen or you recorded from Zoom? Because Zoom automatically removes, I think it automatically removes this window.
I know, but then so Zoom is not 60 FPS to begin with, which means if you upload Zoom recordings to YouTube, it does not have HD. And I prefer my videos to be HD. We'll find, like, it takes iterations. Another 10 times and we'll be perfect. Another year of me using a Mac and we'll be perfect. All right, any closing notes while we're still on air?
Great talks.
Thank you.
Thank you, folks.
Thank you so much for this.
Thank you very much.
Thank you.
We'll do it again.